Hi, and welcome. I'm Borislav, and you can find these slides over here. That's is.gd/immutable. A bit about myself. I do mostly C++ stuff, though I dabble in many other languages. Most of my career has been in game programming, but since 2019, I work at a medical hardware company writing software. So this talk is about this, basically. I do a lot of open source, and you can find me on GitHub /iBob. And now I'm going to do an inspirational, I guess, demo of our software. It's live, so I got it running over here. And basically, ViewRay creates installations for cancer treatment. So here we have some patients, and they're diagnosed with cancer. I select one of them, and I initiate treatment. There's been a plan already done for that patient. Right now, what you're seeing is the MRI scan being taken. So, okay, here we have an MRI scan, and we can compare the planning scan with the current scan right here. Right here, you can see that certain tasks are being done in the background, and we can see their progress. And let's say that we're okay with this current patient position. So we approve the positioning. We're waiting for the anatomical structures to be identified inside of the patient right now, and it's done. So right here you can see it's a 3D scan, so you can see the anatomical structures, and the volume is streaming right now, and it's not that fast because of these really slow background processes over here. So those are anatomical structures inside of the patient, which the software has identified. And one of them is the so-called PTV. So that's the tumor, basically. That's what we aim to eradicate. So we can approve this thing right here. We can also, say, use these tools to tweak and adjust the anatomical structures in the patient. But let's say we approve. Okay, so we're waiting for full optimization right now. I'm sorry if the stream lags a bit, I guess. Why is it taking so long? Did we encounter a bug? Okay, so sorry. So basically, the target hardware for this is like 64 CPU computers and running with, I don't know, the mother of all processors, I guess. And I'm currently running this on my laptop, so it's not as fast as I hoped it would be. Or at least, I guess, the stream is taking some of my CPU time. So we're waiting for full optimization. Basically, right now, the software is trying to predict what kind of dose will be distributed inside of the patient after we finish the treatment, the actual treatment delivery with the linear accelerator beam. It's trying to decide how the dose will be distributed and trying to find the best positions for the beams themselves. So it's basically the plan. During planning, the operator has decided some beam positions, and now the software is trying to optimize them, basically, in such a way that the maximum delivered dose is in the tumor, and certain critical anatomical structures inside of the patient are not being affected by this. Okay, so we get the predicted dose. So if we proceed with this treatment, the software predicts that the dose will be roughly distributed like this. So as you can see, the tumor receives the highest amount of dose. So we're waiting for the QA. QA is basically making sure that everything is okay. We can see here, there's the distribution of the dose inside the different anatomical structures. And here we have some constraints. For example, the tumor should receive those more than 47 gray. Certain anatomical structures like kidneys or liver should receive a dose less than whatever gray. And we're trying basically to work and follow these constraints. And this is the adapted plan. And typically, conventional treatment ends here. So we decide how we're going to treat the patient, and then we start shooting, basically. But of course, if a tumor is in the torso of a patient, there's lots of movement of organs inside of there. There's breathing, there's gas, there's all kinds of stuff going on. So typically, conventional treatment has negative side effects, and these are caused by the beam actually hitting organs which are not supposed to receive a big dose. In our way, our innovative what? No, that was disappointing. I'm sorry about that. That's the I guess what you get with live demos. So in our installation, we scan the patient while treating. So basically, we receive a live video feed with the MRI inside of the patient, which sadly I couldn't show you right now, and I don't know what, and I'm not going to troubleshoot it right now. I apologize. But we receive a live video feed, in a way, thanks to the MRI from inside of the patient. And when the beam when the beam doesn't hit the tumor, or the beam hits an organ that's deemed too dangerous to hit, we just temporarily shut off the beam. And that's how we get the minimal amount of side effects. We adapt while the actual treatment delivery is going on. So what did you just see? You saw software which was started from scratch in 2019, and it aims to replace the current existing software. The current existing software, it's not buggy, I guess. It doesn't have any bugs, but it's actually really slow, and it has, I guess, spaghetti code issues, and it's really hard to add new features to it. What you saw was GUI that runs inside of the browser. So this is a browser that you're looking at right now, and you just saw another tab of it. But the backend is written in C++ 17. So a bird's eye view of the architecture. As I said, a browser client which connects to an application server, and this application server has multiple services and workers. Service is some kind of a process which runs for, I guess, the entire lifetime of the server itself. And in order to communicate with the service, you create a session to the service and then communicate with this session. And you can destroy the session, then you stop communicating with this service. An example of this is, say, the treatment service that you just observed. There's an MRI service which connects to the actual MRI. We have, I said, data service which connects to the database and allows us to get and store different objects. And also we have workers. A worker is something that has a short life. It calculates something and then ceases to exist. For example, the different anatomical structure simplification algorithms that you saw are workers. We calculated those. If the demo had worked, you would have seen like live dose calculation as the treatment is going on. Let's go a bit deeper. So the UI service, for example, it has sessions for clients. It supports multiple sessions as we support multiple clients. So multiple people can connect from their browsers to the same server and participate in the treatment in some way. It basically builds type-erased UI objects from the application state. There's a module to the UI service called the WebSocket server, and it's a layer for browsers, basically. It translates the type-erased UI objects to JSON and receives commands from the browser through JSON again. But theoretically, we could create another module which builds Qt objects from the UI objects, and we can have a Qt GUI. We don't right now, but it's possible. The treatment service that you just observed. So you create a treatment session, and only a single session can ever exist on the server because we have a single MRI and a single radiotherapy equipment, instance of the radiotherapy equipment, I guess. So it has a state which represents the treatment in progress. It fetches imaging data from the MRI service. It issues start and stop to the radiotherapy service. It gathers information about delivered dose, something that you sadly, again, didn't see. But at the end, it saves treatment data to the database. And that's basically what it does. So let's go a bit deeper. These services, they work with objects. And let's see an object, for example. This is a simple bare bones object. It has some data, and you can get and set the appropriate data. But I mentioned multiple threads and multiple processes. So if we just use this object, we'll get races. So a naive approach would be to basically add a mutex to the object. But of course, that's a bad idea because readers and everything will have to wait on each other. So in readers especially. So if we just use our objects built like this, we will essentially be building a single-threaded application. We don't want that. So this C++17, of course, and we have shared mutexes. So we can have a read lock and unlock and write and use the shared locks of the mutex to build an object that looks like this. Okay, let's try to work with this. We can make it more robust, of course, by making the read locks const because they don't change the object, presumably. We can have, also calling read and lock and unlock manually is, of course, not very robust. So we can create some kind of external read lock objects in this typical scoped interface. So basically you lock in the constructor and unlock in the destructor, and that's the right lock. So really, really simple. So in the regular mutex example, I said that readers have to wait on each other. And you might assume that the problem here is that writers will have to wait on each other, but that's actually what we want. We don't want to write at the same time. The thing is that writers will have to wait on readers. And for example, in our anatomical structures, we contouring algorithms, they write. The algorithms that identify those structures, they write. Those calculations, for example, it reads. The UI also reads at the same time. And certain algorithms may also read from the anatomical structures. We don't necessarily need to identify an anatomical structure with an organ. We can create like a boundary, say a 5 millimeter boundary next to the, like around the organ or something like this. So we determined that we don't want readers to wait on writers. And the typical solution to writers to wait on readers, sorry. And the typical solution to this is, of course, this. And this is a cow. And yeah, copy on write. Basically, a lot of languages implement copy on write at language level. For example, Swift and many others do something like this. You have your data, it's a shared pointer. You can always, at any moment, just read the data as it is. And when you want to write on the data, you receive a mutable reference. And in this case, we check whether there are any other references to this object around. And if there are not, we can just return the actual object. But if there are, we perform a copy on write. So that's an object copy here. So let's rewrite our object in the same way. That's basically the exact same thing called object wrapper. But the problem here is, how do we refer to objects? So let's look at this example. We have an object. We have a GUI thread, which basically has a loop which reads the object continuously. And then we want to write to change something inside of the object. That's it. But the problem is that after this line, so after we change something in the object and presumably performs a copy on write, then the object is lost to the GUI thread. So it only has the read-only copy. So it will never be able to get the actual write object. It has a copy of the read-only object. So to work with this, we can create something called object handle. An object handle can be a shared pointer to an object wrapper. Why not? So we have a shared pointer inside of a shared pointer, but I guess it's fine. So now when we have handles, we have a tiny change to the code itself. The object is now a pointer, so we must access with an arrow, but then the object is always the same. But during this line, we presumably change the shared pointer. So we replace the shared pointer with another one. And here we read from the shared pointer. So we read on we have a race on the shared pointer itself. So to work with this, luckily shared pointers have atomic stores and loads. So to work with this, we just can use those atomic load on the read and atomic store when we are copying and writing. So that's a tiny change to our code then. But during this line, we race on the data of the object itself. Of course, after all, if we decide not to copy and write the object at this point and start changing it, and the very next moment the GUI thread starts reading from the object, we race on the object's data. So what can we do? We can create write locks. So oops, what happened here? I'm sorry, I think I have the wrong slides here. Oh my God, this is a disaster. So, what? Okay, so we can bring back locks basically, yeah, and we can have read locks and write locks to our object if you raise on the data itself. And now we can write lock the object here, and we can read lock the object right here in order not to allow basically the, okay, so yeah. The solution here is to always copy and write. I'm sorry about that. So to always copy and write. So when we always copy and write, we have no problems. We have no data races. When we always copy and write, when we always copy and write, we don't need the read lock. We do need the write lock. But when we always copy and write, when we change something, we don't care what the readers currently have. They will continue using their old, outdated copy in a way, and they'll continue reading the old copy. And when they're finished with it will expire, and the memory will be released. And the next change will again copy and write and copy and write and copy and write. And we may deem this okay, because if we're okay with copy and writing, like copying objects occasionally, then we might as well be okay in copying objects always. Why not? And this can totally work, right? If we promise to write from a single thread. So what if we want to write from multiple threads? We can kind of think about making the write object thread safe, but in this case, we will lose the idea. Like writers won't have to wait on each other, and then there will be no notion of the correct object, of the real object. So this is an appropriate place, basically, to bring up the heavy artillery and add an access mutex. So we can add a mutex, and then we can write lock. When we write lock, we lock the mutex, and when we write lock, we unlock the mutex, and writes are synchronized, and they happen in a certain order. And this is basically what we call immutable objects. Why immutable? You can think of it as you do of string view. You don't change the object itself, you replace the object, and the original object remains as it is. In this case, you replace it with a copy. Like string view has certain operations like the replace or append or stuff like this, which will return another, not replace, but like not replace. String view is immutable, so it doesn't change the actual data, but say it gets a substring view for this. So what if we do want the optional copy and write then? And I do have slides for this, but I'm not going to present them in the interest of time, I guess. So let's decide that we are not willing to pay the price, which we will if we have an optional copy and write. We will decide to live with the always copy and write part. So, oops. Let's improve the terminology right now. We call this read, but read is too generic. I mentioned that when we always copy and write, the moment that we get a read, a read lock of the object, I guess, even though read lock is not needed, but the moment we call read for the object, we receive a copy, which in the very next moment can be outdated. So detach expresses this functionality much better. Like detach means that when you get a detached version, that's not the object anymore. It's not a handle. You don't. It will always remain the same. It will always remain the same and immutable. If you make changes to the original objects, your detached version will always remain the same. And write lock is also, I guess, too generic. So we can rename it with I don't know, begin and end transaction. So that's basically what we're doing. We are creating, thanks to the mutex, an atomic transaction on the object when we do this. And we can rename the mutex, of course. And while we're at it, why not add an optional way to store the transaction? So if we can decide to cancel the transaction, in this case, we just won't touch the object whatsoever. So our immutable objects so far, we have atomic transactions, which are synchronized writes from any thread. We always copy and write when we do a transaction, but we have the fastest possible lockless reads by detaching. When you detach from an object, you get your data and you work with it, and then you throw it away, and that's that. And yeah, the detached object is possibly outdated. You cannot rely that once you detach an object, it will be the current state of affairs, basically. But every reference to a detached object is safe and valid and immutable forever. And yeah, what we did basically can be called a glorified shared pointer wrapper. But as we'll see, it kind of leads us to a different way of thinking. And indeed, when we first started working on our objects, we didn't think much of it. It took us roughly a year and a half to get to our object's current state, so of planning and designing and tweaking things. And hopefully for less than a year, I'll be able to explain what we do. But we were like, okay, that's a nice thing. But we started pursuing the slides that I didn't present, the optional copy on writes. But this is basically a lot like React.js because our graphical user interface is in a browser. We did have a lot to do with React.js and many other actual browser front-end frameworks are similar. But we started thinking, okay, well, this is a lot like React.js. And what is React.js? Basically, I'm going to do the shortest and possibly most useless presentation of what React.js does. It's basically a GUI library for single-page applications. You take a state, like, I don't know, a plain old JavaScript object, a POJO. And based on the state, you create the DOM, the elements and the elements which comprise your web page. And that's it. As I said, the most useless presentation, isn't it? But let's see an example. So let's see an example with one of our states. Of course, our installation doesn't necessarily need to be used for treatment. It has an MRI attached to it, so you can use it for plain old imaging, like a regular MRI. So let's try to envision what this state might look like in JavaScript. So we have an imaging state, we have a patient, we have an image with some data like named nodes, size, and buffer with the actual voxels of the image. And we have the table position, which we can move so we can adjust the patient in the best possible position. So, and to build GUI, we call the build GUI function. And that's it. It will produce the appropriate DOM, the appropriate web page for this state. And it doesn't need anything more, it only needs the state. So if we want to change the state, we can have a JavaScript function like this. So we can return an object which only addresses certain elements of the actual state. And thanks to JavaScript reflection, this will be appropriately spliced onto the state. So these are two simple examples, like set image name to some cool image and shift the table to some I don't know, to relative position based on the previous one. So how do we splice objects onto the state? Let's see the set image name function. It has an image, a name, okay, and thanks to reflection, we can find that this addresses image, then name, and only change the name. So JavaScript objects are a lot like shared pointers. For most intents and purposes, they are shared pointers. So a JavaScript object, if you compare them, it will compare their addresses. If you create a new object, that's basically a new instance of said shared pointer. And they're mutable too. So we can do this with no problem. We can find the name and we can change it to cool image. But what happens then? For example, let's have the old state be something. We can splice the set image name function onto the current state. And then we can assert that the old state is different from the current state. But we only changed the name, as John Bon Jovi said. We only changed the name, so the state, the actual root object, is different. So instead, what React does is it changes every object performing shallow copy on writes. So if we change the state, we create a new state, we copy everything from it, but only the addresses. So it will receive, in the initial copy, it will receive the same patient, same table. Then we change the image. The patient and the table remain the same. So if we compare the old state's patient with the new state's patient, it will be the same. But if we compare the old state and the new state, they'll be different. If we compare the image and the name, they'll be different. And everything's fine right now. So how does this help? for example, it does help with building GUI. We can memoize certain elements of the state, and if, for example, the state hasn't changed, we can return null, so make no changes here. If the image hasn't changed, we can return null, so make no changes here. Otherwise, we can return some kind of a DOM object at this point. And this is optimization, isn't it? And then we said something like React.js style state in C++. That would be pretty cool. And then, of course, many people at this point would ask, but why? Like, why would it be cool? The thing is that, imagine this. In C++, we can build a GUI like this. We get the state, we build GUI. It works. But also, we can run workers. We can get the state, we can run the bladder worker, and then imagine these are different threads, and it will start finding the bladder of the patient, find the femurs of the patient. It can calculate the electron density, for example. And those threads will work and they'll be fine, even if we make changes to the state itself. Even if we make changes to the image, they'll continue working with an outdated version of the image, but we wouldn't need to synchronize them at every possible point. And also, undo and redo is pretty easy. For example, if we create an undo action and we set the bladder for this undo action to the current one, then we apply the manual user edits to the bladder, and then we can set the current state of the current version of the bladder to the undo action. That's pretty easy, and it comes naturally, basically, to create undo and redo actions with this. But there's one thing that's much more important than all of these. And that's integration testing by unit testing. And what do I mean by that? So here's the thought. If we magically create our objects and we have built the build GUI function in C++, what if we do that? We can get some predefined state, something hard-coded in our application. We can call build GUI, and then we can assert that the GUI that we have currently, after calling build GUI, is the one that we expected. That's a nice test. That's really nice, actually. That's the best way to test something, a unit test. And in this case, what if we have some predefined state? What if you run, I don't know, a treatment function of sorts, which receives another function, receive new image from MRI with this image, and then applies this action in some way to the state? Then we can assert that the deep compare of the current state is the same between, and the expected state is returns 1. So I didn't express myself really clearly here, but you get the picture. We can test that the treatment with the action receive new image from MRI works okay. And this is big bang integration testing. So we have the entire treatment logic inside of the treatment function, and we test it. And that's big bang integration testing, when you have the entire thing and you test it as it is typically frowned upon. So people prefer, for example, bottom-up integration testing. And bottom-up integration testing will be to test a certain submodule of the treatment. And in treatment, we have imaging. If you remember the first part of the treatment, we started by taking an image from the patient. So we can test the imaging with the exact same receive new image from MRI function and deep compare the imaging state. People also like top-down integration testing. So if we, create the imaging function, which is a mock, we create a mock of the imaging function that instead of connecting to the MRI, it just loads some kind of image and then adds it to the state, then we can mock certain elements and just test treatment with its submodules mocked in a way. This is pseudocode. Don't be too harsh on it. But basically all forms of integration testing are possible. And how can I express myself more clearly here? The thing is that if the application state is in a single object, then everything the application does can be expressed as a pure function. And like this one, pure function, do something with the state and return the new version of the state. And pure functions, we know how to test. Pure functions are unit tested. You don't need complicated integration testing scripts. You don't need complicated setups. We can test pure functions. it would be really great to have pure functions, to have the entire logic of the application inside of pure functions. That's what, for example, Haskell programmers love. You can integration test by unit testing. But moreover, since all modules are pure functions, then mocks are trivial, as you saw. You just can rewrite a complicated function that does complicated stuff on the state itself. You can rewrite it with some kind of hard-coded value. And if the entire state is an object, is a single object, then fuzzing, easy is perhaps an overstatement, but fuzzing, like creating random values, random valid values, is least feasible. We have an idea of how to approach fuzzing in this state. And since it's a single object and we can serialize objects and we can save them and load them, for example, if we crash and we have somehow stored our latest state, we can resume from the crash as if nothing happened. We can store continuously certain versions of the state, not every version of the state, then at least certain ones. And then we can have some kind of jump in time debugging. Like we can just load this state. I have a bug right now. Okay, so what's the previous version of the state? Let's rerun it. Let's see. Let's find the bug here. So if we weren't sold at this point, then we were at least intrigued. Anyway, back to the objects. So this glorified shared pointer wrapper, how does it compare to React.js? So we have shallow compares, of course. Shared pointers are compared by address. And note that this is not string view anymore. String view is compared by data, by the contents, by what the string view points at. And we copy and write on every change, much like React does the splicing, like changes every node of the state tree. And detached references are safe and valid forever, much like React's objects. So let's try to build a state in C++. But first, some minor changes to the object, I guess. First of all, we now know what the object holds, and the answer is something. So of course, it's a template. And we don't need this wrapper part of the name right now. Okay, it's a template. Okay, so we can just call it object. And the thing that is inside of the object, we can just call data. And we can call the transaction thing transaction data. So minor changes. And again, what used to be write log before, we now call transaction. And we can make use of the fact that we can optionally store and or cancel transactions, and just if there are no exceptions, don't store the transaction. So if we throw an exception, the transaction is canceled while doing the transaction itself. That is. So let's build a state in C++. We have the same patient data with orientation and weight of the patient. We have image data with all the jazz. We have table data and everything. And we can just create an object from this image extent, can't we? This is a terrible idea, though, because when we do copy and write, we copy everything. We copy the huge image buffer. We have copy strings. We copy, even if we change the progress of the table movement, we need to copy the whole image buffer, which is tens of megabytes. Okay, not a good idea. So let's are more objects, perhaps. But again, if we change the progress of the image in this case, and image is an object right now, if we change the table, we won't change the image. It will perform a shallow copy and write, but the buffer is still copied if we change only the progress or the name. So that's not a good idea. So let's make everything an object, I guess. But the float is not. Why would we make an object out of a float? Why would we carry the whole shebang of shared pointers for a mere float? So some objects is, I guess, the answer. And here we come across one of the first issues with this pattern, I guess. It's hard. It's hard to come up with a good structure of the state. It's actually the most hardest thing to do in this case. But okay, let's say we're happy with this. Let's try working with it. So in JavaScript, we had the set image name function, and we set it with the image and name with some cool image. And what do we do now? We have transaction of transaction of transaction, transaction of the name of the image of the state, okay, equals cool image. And that's a lot of transactions, so it's not really nice to write. Okay, but we can live with this. But each transaction, if you remember, does a mutex lock. So that's 3 as I see it, recursive mutex locks, which is again not necessarily terrible. It's in any case, it's very dangerous to have deadlocks in this case. Like it's not forbidden to make transactions out of order in this case. So we can detach something, make transaction, and then we detach something else, make another transaction. It's dangerous. But that's not the worst part. The worst part, if we have an image, and that's a lot of detaches here I see, but we can perform a transaction on this image, on the image's name, I guess, on the transaction on the image's name, and set it to something different. And let's assume that the previous value of the name wasn't something different. And now we can get the image from the state again. And when we compare the values, oops, both are something different. That's because, and this is really thread safe. It won't crash or anything. But the thing is that when you, in a way, every object is an object handle. So when you perform a transaction, the owner of the object continues to store reference to the object handle itself. So an object handle's promise was that it is the real object. When you detach from it, it gets you the current contemporary version of the object. So we broke the detach promise. Actually, in this case, detach doesn't mean detach. And that's not the way of React.js, and that's not something that we want. So I did say the root object word. In this case, let's make our object a root object and split it. Let's make the other parts of an object nodes. And the node is something different now. The node has some, I don't know, ways to get the data, like const access to the data, and it has non-const access to the data. And when you do non-const access to the data, when you want the data as a mutable reference, you copy and write. And the copy and write is really simple. And there is no need for atomic stores here because it's always inside of the locked mutex of the parent object. And we can have, I don't know, a nice way to get the actual data inside. And it as a shared pointer if we want. So now, our imaging state is a root object which is composed of nodes. And now to set the image name, we have this kind of code, which is much nicer than transaction of transaction we used to have before. And it will appropriately perform a shallow copy and write on state, image, and name. And all the other nodes will remain the same, the same addresses. So let's make a test. We can have the exact same transaction as before. We can check that the state is different, the image is different, the image name is different, and since it's a node, this is an address comparison, and we can even compare the actual values inside, and it's different. And this is the React.js way. But there are some problems with it. For example, if we have this, we perform a transaction for the image, and we set it to some cool name, like we used before. The thing is that the operator asterisk of name, of the node name, will perform a copy and write. So we copy the old name into a new value, only to replace it with cool name. That's not nice. And also, if we have a transaction which changes multiple elements of the state, for example, like this, then the non-const arrow operator of image will perform a copy and write. So we have two copy and writes for the image. And also, if we have a transaction which does something conditionally, if we test if the buffer is empty and we can set the name to the image to empty, then if we don't send the image to empty and just like the if is false, we do a copy and write even if we change nothing. Like the non-const overload of the operator the arrow operator will perform the copy and write anyway. And here is a library that we use, that I've written and I've open sourced it. You can find it at GitHub, iBob Cusco. And it basically deals with those problems. And I have slides for how we deal with those problems, but I will skip them and just go on. Thanks to Cusco though, when we have this transaction, it overloads the assignment operator, so it won't copy and write if you assign. It uses some clever tricks with copy constructors, so it it basically knows when an object is already copy-on-writed inside of a transaction. So image will only get copy-on-writed once in this case. And it introduces this .r. It's not very nice, I know, but this is basically a way to have a const reference to the data inside without doing copy on write. So when you want to only read from data, you use this. And there are no copies here. And there are more problems, though. So if you want an MRI study is basically a collection of images. You take a patient, you take a bunch of scans from the MRI, and then that's an MRI study. And when we want to add another image, or when we change the state at this point, or when we change the MRI study element of the state, at any point we need to copy the vector on every change of humongous images and everything. So we don't want that, of course. So let's say we make the vector a node. But now when we add or remove or change the images inside, then the images will be copied. So of course, we know the answer. Let's make the images nodes. And what do we get here? We have the transaction, so we add a new image. First, we copy the state, and that's something we expected. That's fine. We expect to copy the state in this case. We copy images, which is, I guess, we need the old images in order to add the new one to them. So that's fine, I guess. But the thing is that in placeback needs to reallocate in this particular case. Okay, so it needs to reallocate. That's something that's bound to happen at some point. But when it reallocates, what does it do? It copies the images. And this is something that we don't want to live with. And to avoid this, basically, you need to create custom container wrappers to help you. There was a C++ 2017 talk, like, I forget the exact title, like Next Level Immutable Objects or something. And they dealt with how to create string view style immutable objects out of vectors and everything else. And basically, you need to re-implement it using shared pointers. For example, we can implement in placeback. And this is a really naive and stupid implementation, I know, but we can just reserve, we can create an empty vector, we can reserve the appropriate size, and we can then assign the old vector, but know that it won't reallocate when we in placeback. And of course, you can play with this. You can reserve more than you need, like vector actually does. When you resize, it doesn't necessarily allocate +1 element to the ones that you have. And you need to do this for every other container that you use inside of a state. In our case, this was really simple because we only use vectors inside of the state. And strings, of course, but we never do any kinds of fancy string operations. So we actually use plain old std strings in the state. And we only have like vector, that specialized vector class for this. But that's a lot of allocations. So imagine this transaction. We set the progress value to something, and we do it like multiple times per second. And each time we do this, we make an allocation for the state, imaging, the images, the progress, the value, and whatnot. And so far, in our case, we haven't done anything about it. We live with the allocations. You can mitigate it by making a better state structure and something really hard, as I said. We're thinking about using custom allocators. We're even thinking about re-implementing shared pointer. And that's probably something that we'll end up doing because, for example, we haven't yet found a use case for weak pointers. And if you don't need weak pointers, you can create something like an intrusive shared pointer. And because we have nodes, they we control the actual data inside. We can basically create an intrusive style shared pointer, which has the shared block closer to the actual shared pointer, not with another hop through the shared data. So anyway, we're still gathering information about this. We currently use plain old shared pointers and plain old allocation. But that's also a lot of copying here, isn't it? Like, imagine the function said image voxel. As I said, an image, an MRI scan of the patient is a 3D image which can be tens of megabytes big. Do we want to copy tens of megabytes of the image just to set a single voxel? And the answer is probably no. And this is a real limitation of the current implementation of this pattern, I can say. We just don't do that. We don't have set image voxel functionality in our code. We could do, I know, a mutable placeholder inside of the state, which uses conventional locks, an immutable placeholder, which uses conventional logs to an actual mutable object, somewhere else. And we actually do use this when we do manual contouring. When the user manually tweaks the anatomical structure inside of the patient, we actually have immutable placeholders in the state which communicate with mutable objects in the background. And that's not nice. That's one of the parts of the code that we don't really like, but otherwise there'll be a lot of copying. So that's a real limitation. And if for example, if you're considering using immutable objects and this is everything you do, like changing huge, humongous objects, that's probably not the right pattern for you. What about reuse? I mentioned reuse. For example, we have the really nice function should_take_scan, which checks if the scan of the state is empty and the user requested the manual retake, and it returns whether we should retake the scan. And we want to use it on our imaging, which is okay, nice. It works with imaging out of the box. We want to use it with treatment, which also has imaging inside, and it's called imaging. And say we have a diagnosis workflow, which also has imaging inside, but it's named phase 1 because someone decided that's the best name for imaging inside of diagnosis. So how can we use should_take_scan in this case? And what we have implemented here is queries. So a query is, I'm not going to get into how we implemented queries. You can, I guess, infer it by how we use them. A query is something that takes a named functionality and works with it with the state. So basically a query, get imaging from the state, and it knows how to get the imaging from different states. We can chain queries. So for example, if the image can be in different places here, we can have get imaging with get image, I guess. The nice thing about queries, since they're templates, they can work with mutable states too. So we can reuse the same queries if we're changing the state as it is. So it doesn't necessarily, they're not necessarily read-only, those queries. So currently we have React.js objects, React.js style objects in C++. They are immutable objects based on ref-counted pointers. They make shallow copies appropriately. They make shallow compares appropriately. They allow for shallow compares appropriately. And they basically are states composed of nodes. They're trees composed of nodes. And we have special nodes for continuous vector in our case. We allow queries. And as I said, it's not necessarily the best approach for every situation. But with integration testing via unit testing, it has much potential, I think. And that's the end of part 1, but thanks to the fact that I skipped some slides, I can continue with part 2. And the thing is how we actually make use of these objects. And we have actions. So basically, since we're implementing React, we could also re-implement Redux. And Redux is a really simple library which works with many different types of web frameworks. And it's it's an immutable state library which helps you add an action to the state. I won't get into too much details, but an action basically is something that changes the state. For example, set the name of scan N in the MRI study of the patient. Receive a new delivery frame, which has a lot of stuff in it, like an image, dose for the current frame, the confidence that we're doing the right thing, that we're hitting the tumor with the beam and we're not hitting different organs. So that's a lot of data for a single action. And of course, it can be set the entire state to this particular thing. Let's see an example of action. This is set name of scan, so it obviously has the data. It queries that mutable query here. So we try to get imaging from the state. If we can set the name of the scan, for example, that's some kind of a check that we're making. We do it. Otherwise, we throw an exception, and this way the transaction will be canceled. So basically, all actions are applied with a function like this. It creates a transaction, runs the action, catches the exception, and I don't have time to get into our error reporting. So here we either notify the user, for example, if it's a user action, that their action is invalid, or we can potentially add a fatal error to the state. Long story. So can a valid action lead to an invalid state invariant? That's a good question. What if we want to enforce unique names? What we want to enforce that every image inside of the state has a unique name. we could do it like this. Like we could set the can set name of scan function, take the name, and it will return false if it's a duplicate name. But the problem with this is that there is no way to check the validity of the state unless we call this function. So if we have the set entire state function, we won't be able to check if all the names are valid. So what we do here is we have state guards. A state guard is basically a function which checks if something is valid inside of the state and throws an exception if it isn't. We can say have overarching state guards which take care of a lot of other smaller state guards at this point, and any one of those can throw an exception. We can check if the imaging is valid with all images are valid, all images are the same size, and stuff like that. So this leads us to an app, basically. An app, what we call an app, is something that has a state and a bunch of state guards with it. We can create it like this if we want to compose with some kind of type erase state guards, or we can create a concrete application like this, like a treatment application, which checks the patient, the imaging, the delivery, and every other thing inside of the patient. So what we do in this case is apply action. It takes an application, not state anymore. We do a transaction on the state and then run all the guards. And that's a lot of guard calls. Because imagine the example with the progress. So multiple times per second, we set something and then we run like a humongous amount of guards. Well, a humongous amount, probably in the hundreds. And that's then a lot of guards, like they reuse, like certain guards can be reused, like certain master guards can call the same guards inside. So we'll be checking the same thing over and over again. And what we do now is we skip the guards being functions. So the guards are actually objects which have they memoize what thing they last validated, and if the thing they last validated is the same thing that they're trying to validate right now, they just return and assume everything is okay. And that's not nice, of course, because guards are now not pure functions anymore. They're almost pure functions, but of course they're objects which have their own state, so they need to be managed. It's not as simple as calling a function in this case. We do have R&D for this, and we're seeing some promising results if trying to memoize the guards and even queries on the state itself. So once you run a query or check a guard, the result of it can be stored in the state itself, and then running the same thing will return in the fastest possible fashion. But again, that's something that we currently don't have. We're working on it. We also have pub/sub. So that's really simple, not too much detail. Basically, when you end a transaction, you have some kind of a new data, the data that's been created by this transaction. And when you store it into the actual object itself, you can also give it to this new data. And if we have new data, you can notify all the subscribers to our object. That's really simple. The thing is, the key part here is that we notify for each state change, but not while locked. So presumably, even though we don't have a single example of this, presumably you can create a transaction in one of your notification functions, in notification handlers for the state change. Let's see a small example of building GUI, of how the UI might work. So we subscribe to the treatment state with the UI thread, and we wake up when we create a change. And there's nothing more to do actually, because when we run the UI thread, we wait until we're woken up, and then we build the GUI, and we're absolutely fine if we skip states, because if we skip states, then the user is probably not meant to see them things happen so quickly. For example, if the progress gets updated 5 times and the user sees only the first and the 5th, it's fine. So when the user runs a command like set image name, we know what to do. Like we push an action to the treatment session. When the user runs a command like calculate the bladder here, what do we do then? We don't have the bladder at this point. We could synchronously call the bladder calculation function here, but that's not what we want to do. We have fancy workers that we want to use here, right? We want to start bladder calculation. And that's when we get into the really multi-threaded stuff. The thing is that let's imagine the user, the actual operator, the human operator of the machine is a C++ process. Then, what does this process do? It has its own state, its brain state. It's the state of the brain of the human operator. And based on the brain state and the observed application state through their eyes on their screen, they make a decision to set the name. I don't like this name right now. I want to set another name for this image. They run some kind of a function to make this decision. And if the decision is to make an action, we push the action to the application. So that's the thought that we really liked. And basically, that's the way services communicate with us. This is a way to translate declarative code, which is the state, the brain state, and the observed application state, to imperative code, like run this action. So the small example for this will be like the bladder observer. That's something too narrow to actually exist in our code, but let's say we could create something like this. If we have a currently running bladder calculation, but also the image of the state is not the same image that we are running this calculation on, then we abort the calculation. Else, we're doing what's correct, so we return. So if the bladder, if the bladder in the state, if there is no bladder in the state, we start the calculation. If the user requested the manual bladder recalculation, we run the calculation, and that's it. And so basically we would implement this function by setting the manual calculation requested element of the state. The action would change this element of the state. So basically this means that our workers are managed. It's not simply running a std thread. Workers can and should be named, they can be found, they can be started and aborted. They have their own state, basically. And there is a state which represents all workers currently running. That's not necessarily all workers in the application itself. It could be all workers for a certain service. Like we don't mix the workers for the MRI with the workers for the auto contouring for the identifying anatomical structure inside the patient. So here we can think of what to do with their result, and we know that we shouldn't just push an action and abort, because if we just push an action and then abort, in the next possible moment, we will rerun the same thing. So basically how we collect the thing from the worker is when the action for the worker job done comes here, like set bladder, we check the worker if it has some result, and only now is the bladder work complete. That's basically about state observers. They run in many, they run after every state change, and then potentially be running many threads. And that's the way how services communicate, through state observers. I have some really short example of tests here, but in the interest of time, I'm going to skip them. We can talk them over later if you want. And so basically, as a conclusion, programming with immutable objects is not a solution for every problem. We found that programming and design, and especially designing of the states themselves, is really hard. And it can be overly verbose, like you write everything over and over again, but that's not necessarily bad. Like being overly verbose is basically writing your specs in plain English in code. The performance is not great, granted. It's not terrible either, but if performance is absolutely critical for the state changes, that's probably not the way to go. And we're working on improving it. But the thing is, it has awesome testing and debugging power. And in fact, from all the pieces of software that I've worked in my life, this is the one that I'm most certain that the business logic is doing what it's supposed to do. Like its business logic is following the specs. So thank you. I'm sorry, there is not a lot of time for questions left. Yes, I've seen other immutable object library, but for example, there's a question if I've seen Immer for Juanpe, I guess, Bolivar. So Immer is an immutable object in the sense of it's library for immutable objects in the sense of string view. Or a vector or the thing that the example I made with the Swift object. So basically, you have an object and you don't change it, but you only have functions on it which return a copy of the object with the changes requested. So it's not necessarily the same thing. Here, the key part here is having shallow copy on writes and shallow compares via shared pointers, something that's really similar to a shared pointer. It's not strictly an immutable object library. It's not like in the sense of Haskell's immutable objects, I guess. When the question is, what problems do we face when a thread produces an outdated result? We throw it away. Yeah, typically this will lead to an exception, like outdated result. So we will throw it away. We won't try to merge it. And in this case, we will hope that whatever triggered this calculation, which is now outdated, will be run again and trigger a new calculation. So, for example, if there's a state observer which watches the image, and if there is a new image, it runs the auto contouring calculation. So in this case, if there's a new image, we might eventually end up receiving outdated contours. We will throw them away, but we know that the observer has actually run for the new image, and new auto-generated anatomical structures are on their way. So that's basically what we do when we receive outdated data. Since everything is shared pointer, do we see a negative impact on cache friendliness? Of course, it's cache friendliness for this particular data structure is terrible. Even if in our wildest optimization dreams with custom-made allocators, the cache friendliness will be terrible. But this is something that's relatively low velocity. So state changes typically, in our case, happen some tens up to tens times per second. So the thing is that we maintain a robust and reusable and then serializable state which describes what the current situation in the application is. When we calculate structures, we don't work with state there. You have a plain old vector which has really cache-friendly image voxels inside of it, and algorithms from it. They start different threads. But the thing is, the result they produce is then applied to the state. So when we do need high performance, we can get high performance in the workers. But as I said, massaging the state is not very performant. But again, if we're talking about tens of operations, tens of state changes per second, then it's absolutely workable. And the robustness, the security that you get with writing this code is great. React.js is an inspiration of sorts. React.js, the question is, how does React.js compare to our library? React.js is single-threaded. So most of the problems that we are dealing with are trivial there. When you have state observers, they don't need to launch some kind of application. They can run directions right then and there. Yeah, it does have asynchronous operations, but of course, we're not writing React.js. React.js was an inspiration basically for the motto, for the thought, integration thread testing by unit testing. In my experience, design with immutability in mind usually emphasizes safety. What has been your experience regarding program correctness and safety? Yeah, I already mentioned this. I think that this is the most safe and correct software that I've ever worked on. It's overly verbose, that's true, but all of the verbosity and all of the data being in the same place basically helps you. It's not hard to write code with the state. It's hard to design a good and not overly wasteful state object. But once you have it, basically you write specs. It's in almost plain English. You write your code following the specs of the application in the most readable way possible, with pure function or semi-pure functions in the case of state guards. So it was the last question. And with that, I thank you. And sorry for all the mishaps that we had.